Framework. In this presentation, we describe the work necessary to prepare and conduct experimental tests on failure by overtopping of embankment dams. In this case, we present the case of a zoned earth dam. This test was carried out in the scope of the project Dam&DikeCare, financed by the National Foundation for Science and Technology. The experimental facility allows us to test embankments up to ½ meter tall and 1.20 meters wide. In plan view, it is L-shaped, divided into a main channel where the reservoir and dam are placed, a downstream settling basin where the eroded sediments are deposited, and a rectangular channel perpendicular to the main channel and the settling basin, at the end of which the flow exits the facility. It operates in a closed circuit. Water is introduced by gravity from an upstream reservoir through a 150 mm diameter inlet pipe. The discharge is measured with an electromagnetic flow meter. A pervious brick wall is installed inside the channel, immediately downstream the pipe exit, to diffuse the jet that flows out of the inlet pipe and to quiet the flow disturbances. The dam site is placed at the end of this channel, creating a reservoir of about 1.3 cubic meters that can be rapidly emptied through an outlet sewer installed in the channel bottom. The left side wall of the main channel is made of perspex glass to allow for level and lateral erosion monitoring. This transparent wall allows for viewing the dam's internal profile in the case of zoned earth dams. It is thus possible to see all the layers composing the dam, including the bank toe drain, the internal filter, the vertical drain and the core, and its evolution while the dam is overtopped. Downstream the main channel, there is a settling basin where the sediment removed from the dam body are deposited and prevented from going into the recirculation circuit. In the downstream channel, perpendicular to the latter, the effluent flow exits through a calibrated V-notch weir. We now explain the key steps that precede the experimental test. Soil characterization and preparation. The first step concerns the selection of the soils adopted in the embankment body. The selected soils are submitted to geotechnical tests for the determination of their intrinsic characteristics. A pycnometer is used to determine the specific gravity of the soil. The Casagrande test is a standard test to determine the liquid limit of the sample that, combined with the plasticity limit test, allows for the determination of the Atterberg limits. The sieving analysis, combined with sedimentation, allows for the grain size distribution curves of the selected soils. The standard Proctor compaction test is a laboratory method to experimentally determine the optimal moisture content. It generates a relation between moisture content and dry density, called compaction curve. We now explain how to prepare the soils for the dam's construction. The soils must be pre-processed before application. The water content has to be adjusted to the optimal value from the Proctor standard test, since this is vital in order to obtain the highest density from compaction. In clay soils, this is particularly important because they are moulded when wet but become very hard when dry. In addition, some pieces of rock of very high dimensions have to be removed from the sample and clods must be crushed to maximize the soil homogeneity before application. The silty sand used in the upstream and downstream slopes of the dam is compacted with a vibratory plate, and the clay core is compacted with the use of the hammer from standard Proctor test. The hammer is dropped a number of times from a specific height, both previously determined, to achieve the desired density. To define the number of passages with the vibratory plate in the dam slopes and the number of drops of the Proctor test hammer in the dam core, different compaction efforts are performed on 2 layers trial lifts. Cores taken from these lifts are analysed to determine the adequate number of passages or drops. We now describe the construction phase. Experience dictates that uniformity and homogeneity can be achieved if the embankment is constructed with a multiple lift system. The first lift has the particularity of containing the horizontal drain across the dam's downstream slope. In the remaining parts of the dam, clay and silty sand were respectively placed in the core and upstream slope. The remaining lifts are compacted one after the other with adequate scarification to improve binding of successive lifts. Cores are collected from each lift to monitor compaction characteristics during the construction phase. The chimney filter abutting the downstream face of the impervious core is built as a sandy transition to collect the seepage and hence keeping the downstream shell relatively dry. After the last lift is erected, the chimney filter is wetted before compaction to achieve saturation and hence to provide the maximum density of the filter. After all lifts have been raised, the last step corresponds to the final cuts that allow achieving the desired shape of the dam. Note that the lifts form a parallelepiped followed by the implementation of the toe drain in the dam downstream slope. Instrumentation is set up after finishing the constructing of the dam. Monitoring layout. In this dam failure test, by overtopping, we seek to acquire data to characterize the unsteady flow over the eroding dam and its evolving morphology. We also monitor the inflow and outflow discharges and water levels in the main channel. The inflow discharge is controlled by a wedge gate valve placed at the entrance of the main channel. It is monitored with a digital flow meter. Water levels in the channel are monitored with ultrasonic level sensors placed upstream the dam, some near the breach. Water levels are also measured in the downstream channel. Inside the settling basin, water levels are determined by processing the footage of an HD camera. Other digital cameras are placed around the dam to obtain a complete characterization of the failure process. An HD camera was placed above the dam to monitor the breach evolution from the top, allowing for determining the lateral erosion rate. Another HD camera is placed downstream the dam to monitor the breach erosion in the downstream slope of the dam. A third HD camera, placed in the breach vicinity, acquires images to calculate surface velocity maps through PIV. 2 floodlights placed on each side of the channel illuminate the surface flow seeded with white styrofoam beads, thus ensuring good contrast between the tracer particles and the flow. 2 motion sensing devices, Kinect sensors, were used to obtain 3D reconstructions of the dam morphology before, during and after the failure. One was placed on the top of the dam, the other was moved around the dam to obtain a complete sweep of the 3D volume to reconstruct. To assure a common referential in all the 3D reconstructions, 4 targets with known coordinates are fixed to the channel walls. Once the embankment dam is constructed and all equipment is placed, conditions are met for the failure test to take place. On the day before the test, the following steps are taken. The reference grid lines are drawn on the dam downstream slope. This is achieved with a chalk line reel. In this case, they form a 10 by 10 square centimetre grid. A small V-notch is carved in the centre line of the crest to guide the development of the erosion incision in the downstream slope. The main channel is filled up to a level of about 0.20 metres below the dam crest. This level is maintained for some hours, allowing for internal percolation. On the day of the test, all instruments to monitor inputs and acquire data are placed, connected to the corresponding acquisition systems, and, if needed, calibrated. Regarding the HD camera's data, calibration images for PIV applications are obtained after the test. After everything is checked, the test is initiated by inducing the embankment overtopping through the V-notch carved in the crest with a very small flow. During the failure, the flow is interrupted at specific instants to acquire depth images with the Kinect sensors. They are used for the 3D reconstruction of the eroding dam at those instants. An experimental test of this kind, and under these conditions, requires the presence of several individuals to control the water level in the main channel, the water inlet to the facility, the signal acquisition of the level probes and flow meter, the evolution of the dam erosion, to decide when to stop and acquire depth images, and to feed the flow with seeding particles or PIV measurements. To conclude, the realization of this test required the dedication and competence of many professionals of different areas, such as geotechnics, hydraulics, and instrumentation. This shows not only the complexity of the subject, but also the need for a multidisciplinary approach. By documenting every single step of the process, we are able to present a detailed view of the test, allowing experimental and numerical modelers to gain a deeper insight about the test. And we expect that in the future, such approach will become the norm. The measured data sets were used as one of the benchmark tests of the 6th workshop on river and sedimentation, hydrodynamics and morphodynamics on the 2021.